Acids and bases, introduction 14.1. Now the worksheet, I know this is kind of crazy. I could just tell you to do the whole worksheet if you wanted to, because you're able to do it, but I don't want it to be busy work. So do these selected that I picked here. Number 1, A, C, E, F, G. 89, all of it, A, B, C. 90, only do A. And then on 18 on the back, on the other side, I mean, A, C, F, G, H. Now, you can do all if you wanted to. It's not really hard, but it might get to be a little bit like, oh, I don't want to be busy work. That's why I'm having you do just half of them. But anyway, all right. So what's going on in our class right now as you watch these videos? Equilibrium, I'm able to teach equilibrium like in the first chapter when we do gas equilibrium. I go over how to do the beginning math part for acid and base equilibrium. In fact, by the time you've finished all the lessons, if you've done all the lessons from the last chapter, even if we haven't had the test yet, but if you've done all the last chapter's lessons, calculations of equilibrium KSP, KA, and KB, I introduced those, and then KP, of course, for gases, and KC for gases. If you've done all those calculations, you're in great shape for gases, and you pretty much can pass, just about pass, any question on Ka, Kb, or Ksp, which is in this chapter. This chapter is about acids and bases and solubility. But I'll be telling you all the details about it, like what did I just find? You may have done all the math. You don't really understand all what you're getting, what you found there, but in the notes here we'll go through that. Okay, acids and bases, as we said, or I've mentioned, they're an important category of chemistry. Some books just say this chapter is on acids and bases. We talked about them earlier in the year, and I gave you the names of the acids. In fact, you should know what are the 6 strong acids. They are hydrochloric acid, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and HClO4 perchloric. You should know those by memory. If it's not a strong acid, it's a weak acid. In fact, there are different definitions of the acid and base, and I'll go through that here with you. I even wrote this a little bit. If you write down hydrogen chloride, when it's not in water at all, it's only a gas. That will be called hydrogen chloride gas. The only time you call it hydrochloric acid, if you bubble it through water, now you get HCl. That's hydrochloric acid. That's hydrogen chloride gas. You bubble it through water and you get HCl. In fact, if you were to take a big container and you had a tube and you bubbled into here HCl gas, okay, and you kept bubbling it and kept bubbling it, of course it's going to dissolve and make HClAQ. It's going to keep doing that, okay? You would never want to smell this gas. Oh, the smell of that. Oh, it's when I open it, sometimes I get that smell, and it's really horribly strong. You got to use not a vacuum. What do they call that thing? Well, it's a vacuum. It's a vacuum aspirator thing that sucks out the air there. A fume from a fume hood. Or I have something in an old room that my new room won't have that though. But anyway, it's like a little vacuum that it sucks away any vapors. Well, if I were putting this vapor in the water, I wouldn't smell anything at first because it'd be dissolving in the water. But the moment I smelled it, when some of this gas now comes up to the top, at that moment that means it is saturated. I want to bring this up to you. This idea, saturated. That means all the HCl gas that can possibly dissolve and make HCl aqueous is in this water, and now instead of just bubbling the HCl, now it's HCl starting to come out the top here. All right, gas is starting to bubble up the top. Now you know it is saturated, and the correct term for that in Chemica is concentrated. So concentrated means you have the strongest possible acid that you can have, concentrated HCl. I think I've told you this before. If you were to do this with H2SO4, for that one you have to bubble sulfur trioxide gas through there. But if you did this with H2SO4, what would happen is your acid, it would be so strong, it'd be 98% H2SO4. And I think I've told you before when you write net ionic equations that if you have HCl, any of these acids, whenever you write them down, you always break them up. You always break them up completely. That's what a strong acid is. HI in water breaks up completely into H plus I minus, or H plus and nitrate. H plus and nitrate. However, H2SO4, we normally break it up this way, H plus and HSO4 minus 1. However, if it ever said H2SO4 conc or concentrated on the AP, guess what? You don't break it up. It stays intact because it doesn't have enough water to break it up, to dissociate. Kind of a weird thing. That's a small little tidbit that you'd need to know also when you do equation writing. So all of these concentrated acids will all break up, concentrated or less, it doesn't matter. If you ever have any of these acids, they completely break up, even H2SO4. However, if it says concentrated H2SO4, it just stays not broken into positive and negative. It will dissolve, but it's not broken up. Okay? Now, I guess I'm kind of jumping around. I'll tell you, these are acids. An acid, one definition, is a substance that when you dissolve it in water, it releases H+. That's the first definition. So I'm going to go through that in a minute. I left HClO4 off because you're really not ever going to see that on the AP at all. But it is a strong acid. But it also does something called redox. You've heard of that. It does redox and acid. It's just a lot. It becomes very complicated, what it can do. Okay, and very nasty, dangerous, yucky. Okay. Oh, the first definition I have of acid and base is by Svante Arrhenius, called the Arrhenius definition of an acid and base. Oh, and actually I have that little bit about H2SO4 right there, written above it. But there he is. So he says an acid is a substance that when you put it in water, it breaks up into H plus and well, I'll do it this way. It breaks up into H plus and the anion. The general symbol for anion is A. In fact, sometimes the AP uses this symbol. And what this means is, this is your H plus, and that's the negative ion. H plus, H plus 1, and chloride negative 1. Chloride negative 1 is the anion, and that's the H plus. It breaks up into the positive and negative. Now, so that would be an acid because it releases H+. And so HCl, NaOH, gives you HOH and an ACl. This is the acid because it releases H+. This is the base. A base is a substance that releases OH negative. Okay? And then H plus and OH negative, guess what? They combine to give you water, H2O, yay. In fact, if you did the net ionic, that's all you get. If these are both water, aqueous, HCl is aqueous. We break it up. NaOH is aqueous. Okay, I'm doing it real messy. HOH, water, is liquid, but then you get NaCl, and it's also going to be, it's also going to be, I said it, but didn't do it, dissociated. So, cross out all the chloride, cross out anything that's on the left and on the right, unchanged. Na+, and all you have in an acid-base reaction, the net ionic equation is H plus OH negative gives you H2O. In fact, I think it might be safe to say, of all the 80 years of all the equations, they ask you every year to write 3 equations. Now they're going to do that now. They used to make you do 5. Now they can do 3, and they make you balance them, and they ask you questions about them too. Like what's solid, liquid, gas, what's the acid, what's the base, whatever. But anyway, this is probably the most common answer ever on the AP exam for equations, because a lot of reactions can do that. Well, maybe it is. It has to be up there. So they've asked it a lot. All right. Okay. So now you know what an acid and base is according to Arrhenius. And I showed you with barium hydroxide there. Now, strong acid, when we say strong acid, that is an acid that breaks up about 100%. We assume 100%. So what that means is this. If I had I'm going to get an easier number. Let's look at 2. 2 molar HCl Well, if I had 2 molar HCl, if I prepared that in the lab, I bubble the gas through, say, okay, it should be 2 molar. Well, the amount of H plus that I'm going to have is going to also be, well, 2 molar. In fact, all of this is going to go away and convert into that. So if you have HCl is 2 molar, then, in other words, if you want to call this equilibrium, at equilibrium, we say like 99.99%. You're going to have only an amazingly small amount of HCl that is not broken up. Okay? We just say 0. So pretty much 100%. So you're allowed to assume, and you can say this on the AP, because HCl is a strong acid, then since it is 2 molar, your H plus is also 2 molar. Well, how about, I shouldn't even say that. Since it was 2 molar, when it breaks up, the H plus will be 2 molar, and that will become 0. All right. And then that will also be 2 molar if you need to know that, because obviously. But anyway, okay, that is a strong acid. That's true for all of them. And for H2SO4, it's true for the first one. Now, for the weak acids, anything that is not on the list, like let's look at HF, for example. Well, HF, yes, it will break up into H plus and F minus, but it's going to be almost the reverse. Like almost all of it, we'll just say almost 100% of it will be HF. So if I started with, like, say, 2 molar HF, I'll have to calculate it. Now we have to do icebox later on. That's coming later. Well, when it icebox, whatever, at equilibrium, you only are going to end up with, like, we'll say 0.000, let's just make it 0.001 molar of H plus, and you still have 1.99 molar of HF. So what we're saying is you started with 2 molar, okay, it reacted, it broke up with water, H2O, and now you have only that much H plus acid, but all of this is intact. H plus, this is the active ingredient. This is acid, the acid ingredient. And what does an acid do? If you put acid like on your food, what? Vinegar, or juice, lemon juice in your drink or food or whatever. Lemon juice, if you ever tasted it, it's sour. Okay, acids have a sour taste. If you ever got some in your eye, or if maybe you had a cut, or maybe a cut that had healed on your hand, and lemon juice got on it, or vinegar on it, it burns really bad. So it's a stinging, burning. You drink it, burns your throat a little bit. That's a property of acids. What is burning you and doing that is the H plus. Now, really, it's something called H3O, hydronium, but H plus is okay to use. We use both H plus and H3O. I'm going to bring that up in just a moment, the hydronium, in fact, with the next definition. Okay, so weak acids obviously are not 100% broken up. They're more like maybe only about, it can be different numbers. It can be up to even 10%, 11%, 12%. It can be, it can be anything under 100%, but usually it's in the low range. The AP, they're usually 5% or less, if you remember me talking about that rule. All right, number 2, this is the most important rule of acids and bases definition, the Bronsted-Lowry definition. And what they do is this. I can still use HCl on the paper on the next page. I still use this, but I can still have HCl and NaOH. And let me see. I'll put the same equation first to show you how it still works. This they call an acid is a proton donor. Now, what do I mean by proton? Okay, let's watch this for a moment. Let's draw a hydrogen atom. Then we'll draw an H plus ion. In a hydrogen atom, there are 2 parts that are really a proton that's positive 1 and 1 electron that's negative 1. Positive 1 plus negative 1 gives you 0. So a single hydrogen atom has 1 electron and 1 proton. You know that from way back. Well, a hydrogen ion, guess what? H plus ion has lost the electron. Goodbye, electron's gone. So you only have a proton. That's why they call H plus a proton. So an acid is a chemical that gives a proton away. HCl is an acid because it gives H plus. It It donates H plus to the reaction. Okay? What is the base? Well, the definition says a base is a proton acceptor. Okay, proton acceptor. So, watch this. Now, we know that NaOH gives you, the OH negative is what we're really looking at. But OH negative is going to attract the H plus, right? H plus it is accepted by the base. So it takes the H plus 1, the OH negative, how would you say, the base receives it. Or, I'll say proton acceptor. Could say receiver, but oh well. So they come together to make water. So the chemical that gives you H plus is the acid. The one that the H plus attaches to, that is the base. The one that acceptor or the one it attaches to. Now, why do we need this definition? Well, as you're going to find out in a moment, I'm going to write an equation here. Some chemicals do not have, you know what, my computer, sorry, doing some things here. It's been very good lately, and I want to keep it that way, so I'm protecting it. I put a jacket in front of it, and I put it to sleep there. Not on it, but just blocking the chalk dust. Okay, here we go. I'll just jump. You know what? I'm just going to jump all the way over here to this section where we're doing some samples. Letter A. For each of the following, identify the acid, base, conjugate, acid, conjugate, base. Sorry. I'll just do that all together at once instead of, because it might be a little bit goofy going. You can read the other part too and see what I wrote. All right, A, number 1. It says ammonia reacts with water to give you NH4. I didn't want to do that example. Well, you know what? Hold on one moment. I'm going to do it. I need to show you one thing. You're not going to... I gave you that equation. There's another way this can also be written. It's like this. Let me just stall back for a minute. I just realized I got to talk about this for a second. It wasn't in my notes. Okay. An acid, this equation and this equation are the same thing. In this one, we don't write the water in this equation as a reactant. But here we do. But what really happens is the acid gives up an H plus, right? The H plus is actually going to attach to H2O to make hydronium. So this is hydronium, and that's the anion. Here, that's hydronium. H plus in water is not really just floating around by itself, H plus. It has water molecules surrounding it. So that's kind of like when you write H plus AQ, you're talking about hydronium. I just wanted to bring that bit up. And then I wanted to show you this. I really should have put this example. There are 3 examples on the paper, but I'm going to make a number 4. And I'm going to do it first, actually. I'm going to do a number 4 and put it first. It's probably going to pop up in your notes somewhere later on, but oh well. Here we go. So let's take a weak acid like HF, and let's mix it with water. Now, anytime you hear this thing about, and they love it on the AP, identify the acid and the base. Identify the conjugate acid and the conjugate base. If you hear that word conjugate brought up, you need to be reacting it with water. You don't want to write your equation in this form. If you want to try to find a conjugate, put water in there. So HF reacts with water to give you H3O plus and F minus. All right? Remember, just take the H plus is going to attach to the water to make hydronium, which is really true. Every H plus, I mean, if 1,000 H pluses break off, you're going to have 1,000 hydronium. So every H plus that is there is going to be attached to water. Now, it's okay. I know you might get confused why they do these 2 forms. Really, this is just a shorthand for it, is all it is. But this is more complete, especially if you have to identify what's called conjugate. I'll explain that here. So, in this reaction, HF is called your proton donor. Okay, so this is the proton donor acid. It gives away the H plus, proton donor. Okay, now After it donates the H plus, when H plus leaves, what is left over? That is called the conjugate. It's kind of like the alternate form, like alternate personality. HF is the acid form. Take away the H and now you're just F minus. So that's your acid, and that is actually called a base, the conjugate base. Conjugate base. Now, I'm jumping ahead and kind of showing you something. No, this is in the notes here, and I just didn't, I don't know. I didn't like the examples that I have there in my notes before. I wanted to jump to this one. So this is your acid. That's the conjugate base. All right. Remember, that's like think about the anti-form or the alternate personality of HF is F negative. You're the conjugate. And if you're an acid, your conjugate, your alternate form will have to be a base. It is a base. Okay? Now, here is the other weird part. Okay. So this is called a proton donor. Who does the H plus attach to in this reaction? So it donates it. Who does it attach to? Well, it's going to make H3O, right? Plus. So it must attach to this. So if you attach to that, guess what you're called? You are the base. Because you're the proton acceptor. That's the acid, HF, and H2O is the base. Isn't that weird? So this gives up the H plus, and water acts as a base to receive it. And we know the water receives the H plus because look at what they produce, H3O plus. They come together there. So now, this is the base. Okay, it also has an alternate, if you want to say alternate form there. This is the base. It turns into that. And guess what that would be? The acid. This will be its conjugate acid. That's the base. That will be its conjugate acid. Okay. So, you have in a reaction, in an acid-base reaction, according to Bronsted-Lowry, you have an acid and a base. And each of the acid and the base, after they react, what is left over on the other side, the results are going to be conjugate acid and conjugate base. The conjugate of the acid has to be a base. The conjugate of a base has to be an acid. Okay, I know this is a lot. You might have to go back through and think and review this part again. But I'm going to do 3 more examples, and hopefully you'll get the hang of it as I go through all of those. So here we go. First, number 1. See, I didn't want to do number 1 first to explain this because now it's going to look, you're going to see something else crazy here. Something crazy here. NH3 plus H2O gives you NH4 plus and OH negative. Now, let's look at this for a minute. All right. This is probably one of the best reactions to describe why do we need definition number 2? Arrhenius, I'm sorry, Bronsted-Lowry. That is the most important one for the AP, number 2 definition. Because there are some chemicals that when you put them in water, they cause H plus to be produced or released. Okay, that's an acid. But there's some chemicals you put them in water and they cause OH negative to be produced. Well, when these react, look at what happens. You're having hydroxide produced. And we know that's a base, right? It's basic. You're making the water basic. What is doing that? It's actually the NH3. How weird that is. So, here, let's try to back it up and make it a little easier. Which is the acid, which is the base? You got to decide who is giving away H plus. From the beginning, one of these chemicals gives away an H plus, donates it, and one receives it. Can you see that? Which one gives away the H plus? Well, look, because you're going to make NH4 plus. So if I'm going to make NH4 plus, that means, oh, the H must leave water, and it goes to that one. So this is your acid. It's the proton donor. Proton donor. So it's going to give away H plus. Then the H plus is going to attach to NH3. Think about that. NH3 plus H plus. Well, now you got another H, NH4, and now you have a +1 charge, ammonium. That is the acid, and this is the base in the reaction. So that's the proton donor. That's the proton acceptor. You know what? I'm not going to write acceptor every time, but I just want you to see that. Here's your acid. Here's your base. Okay, that's the first part. Now, the conjugate is the alternate form of each one. So I think it's really easy on this one to see NH3, what is this alter ego on this side? Well, it has to be, NH4. Yeah, it looks like NH3. See, it is inside there with an H plus attached. That's a base, so this must be the conjugate. Now, okay, NH4 plus. If this is a base, its conjugate form, I told you, has to be an acid. That is an acid. NH4 plus is an acid. And we'll show you more of why that's true later on. But our NH4 is an acid. By the way, all of these actually can be double arrows. Did I put that in there? Yeah, I did. Okay, because this can actually go backwards. And I don't want to confuse you by doing that too right now, but we'll see it later. That's your conjugate acid. Now, if this is your acid, what's your alternate form of that? Well, it's got to be that one. There's nothing left over. But it makes sense. You give away the H plus, take H plus, H2O. Take away an H, you just have HO or OH negative. And we know that's a base. So it's the conjugate base. Now, just to also, not to mess up your vocabulary here, but it's really more correct to say, identify an acid-base conjugate pair. And the acid-base conjugate pair, NH3 and NH4 plus are conjugate acid-base pair. That's the base and that's the acid. Okay, so you could just as well say, NH4 plus, what is its conjugate? Oh, its conjugate would be NH3, which is a base. Or OH negative is a what is it? It's a base. What is its conjugate? Its conjugate is H2O, acid. So you could say conjugate base, conjugate acid, conjugate acid, conjugate base. So you can really use the word conjugate for all of them. It's just a matter of who you compare it to. So, it's just a vocabulary thing. So base and its alter ego. Well, the word alter ego or whatever can just be conjugate. Yeah. Okay, that was number one. So what you'll be doing in a lot of the homework is just, there's no math in this homework today. You're going to be going through the worksheet and just identifying. You have to really pay attention to what is going on in the reaction. The good thing is they give you the whole reaction. And sometimes even on the AP, this is how it works. And what a great thing AP does is on a multiple choice question, and they ask you to identify conjugate acid, conjugate base, etc. I seem to remember that there's somewhere in here there's going to be a misprint, but we'll see if that's not here. All right, so here we have something reacting. Now, on this one, notice we start with this and water. Okay, H3PO4, and here's H2PO4 negative. Can you tell? Obviously, these two are related to each other. Okay, here's H3PO4, and here, what has changed about that? It has lost something, hasn't it? It's lost an H. Well, that must be the acid, the proton donor. So this is the acid, and that would be its conjugate base, because it's the form without the H. So if that's the acid, now here's the easy. If that's acid, that has to be the base, right? Yeah, and it makes sense. And we saw this in the first problem, the extra number 4 that I added in. This is the base. We know it because look on the other side. H3O plus. You've gained an H plus. So this is the base, and this is the acid, the conjugate acid. Conjugate. I could put conj or whatever. But conjugate acid. The conjugate to that base is H3O plus. Okay, so here was the base, H2O, but now here's H2O, but it's a little bit different, and now it has an H added to it, an H plus, because it was a proton acceptor. Okay, and then the last one, number 3, it says HPO4 negative 2 plus H3O plus. Okay, this might be the one. Let me make sure that this reaction is correctly written. H2PO4, I think it is correctly written, plus OH negative. Yeah, it's wrong. Okay, it is not, it's impossible the way it's written. What it should say is HPO4 negative 2 plus H3O plus gives you H2PO4 plus H2O. That's a mess up in my notes. I promise you that's messed up. Okay, HPO4 negative 2 plus H3O plus gives you HPO2PO4 negative and H2O. All right, so now you can easily see. you know, sometimes it might be easier to say who's the conjugate, who and who. In other words, you look the same, but you're the alter form of it. Well, HPO4 negative 2 and H2PO, oh yeah, obviously those are alter egos. And H3O, H2O, yeah, that is H2O, but it has H on it here. Okay, so we did that part first. We just got the pairs, but now who is who? Okay, which one is giving the H plus and which one's receiving the H plus? Can you tell? Okay, well, look at them for a minute, and hopefully you'll figure HPO4 negative 2 on this side, H2PO4 negative 1. Oh, wait a minute, more than the negative. Here's there's one HPO4, here's there's two H. This received an H. This thing received an H. So if this is going to receive an H, then it must be the base. Okay, because it accepts the H plus. Who did it get an H from? Well, it must get it from H3O, right? So it's the acid. H3O gives away. Think about it. If I take H plus from H3O, I'm left with H2O. So acid, and this is the base, conjugate base. If you want to, you can just the conjugate acid base pair. I mean, you could base, and here's the conjugate acid. So you could actually, I mean, depending on the question, you could even leave out the word conjugate. You could just, I mean, from this name, you could just say, well, HPO4 negative 2 and H2PO4 negative are conjugates. This is the base, and this is the acid. They're acid-base conjugates. H3O plus is an acid conjugate of H2O base. So, in this reaction. Yeah, you can do it that way too. Alrighty, we're almost there. Now, there's one more definition I need to show you. And this is one that the AP says that they're not going to emphasize as much anymore. But I'll show you later, and maybe in one of these examples, that complex ions, you've seen those before, and those are always on the AP. Complex ions can also undergo equilibrium. And when they do an equilibrium reaction, it really is an acid. It pretty much is an acid or a base, but an acid one. Okay, so what is a Lewis definition? There's G.N. Lewis. Yes, the same one that did Lewis dot diagrams. And I always tell everybody an important thing. When you want to identify the acid and the base for Lewis acid, which is the Lewis acid? Which is the Lewis base? Draw the Lewis diagram. In fact, for this one, I might just start off with the more difficult one, because that's the most famous one that people like to see. But let me give the definition first. An acid for Lewis, an acid is an electron pair donor. Now this is the donor, and a base is an electron. Oh, no. Sorry, acceptor. Electron pair donor. My notes are correct, I hope. Yeah, I did. I did it right in the notes, but I just copied it down from my mind, and I was saying it, and Okay, electron pair acceptor, electron pair donor. That is what we mean. Why in the world did they come up with this? Okay, actually, first I'm going to show you an easy way to a reaction to remember it on. Then I'll show you I'll jump up to the example. Okay, so here we go. H plus OH negative gives you water. Which one is the acid? Which one's the base? That's easy, right? Acid, base, and that's your water. Okay, well, for Lewis, here's what you do. You have to draw the Lewis dot diagram. Can you remember to draw the Lewis dot diagram for hydrogen? You put one dot. But if I want to draw H plus, I'm going to have to take away that dot, put a hydrogen, and put brackets around it, +1. Hydroxide Lewis dot diagram. Well, it turns out that oxygen has 6 valence electrons. Hydrogen has 1. 6 plus 1 is 7. -1 charge means you got to have 8. So you have 8 dots. 2, 4, 6, 8, and we put the H on it. Okay, that's hydroxide. And you also have to put brackets. Anytime you have a charged particle, molecule of the charge, you must put brackets around it, or you won't get You won't get on the AP. You will not get credit for that. So that's the acid, that's the base, and that's water. Well, in the Lewis definition, here's what I want you to see that's happening. When H comes together with OH to make H2O, does it fit here? Yeah. H Well, actually, let me draw the OH. I think you can see this. So here comes H plus, no electron. You know, it's all empty, it's valence. It comes over here, and notice it's going to attach to a lone pair. That lone pair makes it the base because it's electron pair donor. This is the base it donates to this, and it plugs it into the valence of this. So it comes over and boom, now they are water. So this received, well, H plus is the this is the acid because it receives an electron pair, a lone pair. Maybe I should call it lone pair. Electron lone pair acceptor and lone pair donor. This donates the lone pair. It uses these two electrons and now makes a bond. It becomes the bond. Okay. Actually, there's a word for that. It's called a coordinate covalent bond. A coordinate bond is when all the electrons in the bond come from one species. These two donated it to the H plus. You could think of it that way, I guess, but I'm kind of jumping ahead to some stuff. All right, so now I want to go over on the examples. I might zip through them, but let's go to the A1, 2, go to part 3. And it said, I want to do number 3 first. Not part 3. It says BF3 plus NH3. Oh, and I didn't even tell you what it produces. This can actually be on equation prediction. And this one just gives you this, BF3 and H3. You think, well, what did you just do? You just put them together. It's a Lewis reaction. In fact, you might remember that when I showed you chemical reactions. When you can't figure out, like double replacement or whatever, just add them all together. But hopefully you'll notice this is a very famous format. I mean, it could be BF3ClNH3. It could be BCl3NH3 also. Any halogen can be there, and any hydrogen or halogen can be there. Any hydrogen or halogen can be there, and this is one that you should just kind of memorize. But if they were to tell you, probably on they could say, predict this reaction, identify what is a Lewis acid. Okay, so draw the Lewis dot diagram for BF3, and hopefully you're really good with this. You're like, oh yeah, 1, 2, 3, fluorine, fluorine, fluorine. You put the 3 dots, the shortcut, put fluorines all around them, and make sure the fluorines all have their dots. Now, if you're doing for a grade your Lewis dot diagram for AP, make sure you show all the dots. NH3 look like this. In fact, I'm going to draw it sideways just to make it real clear to you, and I think you'll see, oh, okay. I say sideways, but can you see that those two are coming together to give you F? You really should kind of memorize this diagram and remember that I could, instead of fluorine, I could put anything in group 17. I could put chlorine, iodine, bromine. I could even put an HHH there if I wanted to. And that's going to bond to N. And the same thing with the NH3. I could put HHH, Cl, 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 FFF, Br, Br, Br. This is just a boron and ammonia. Boron and nitrogen undergo this kind of bonding. Phosphorus can also do it, by the way. Okay? There are some others, but these are the main ones. But anyway, but look at what's happened here. Can you tell who the acid and the base is? Well, who gave, the one that gave the lone pair is going to be the base. And that one, that had the lone pair, it plugged it into here, and then just flipped that around, and that became the bond. So that's your base, your Lewis base, and that's your acid. And yes, there can even be equilibrium with these things. Okay? If I go back to page 1, I don't want to draw a Lewis dot for all of these things. I don't want to do all of it, but I'll do a few of them. I'll just see. Actually, this is pretty easy. HCl and H3. That one's too easy because HCl is the acid. That means that must be the base. And so that one's going to work out okay. The way you would kind of draw it though, because you have NH3, well, you remember this is going to break up in water. So you'd have H plus and Cl minus, and that doesn't react with it. The Cl ends up being a spectator. So really, it's just the NH3 is going to plug into the H plus. Oh, I should do it that way for Lewis dot diagram. So that's your acid. That will just plug into that to give you, on the other side, I should tell you, you're going to get NH4Cl. But since you're in water, it's going to be, well, you know what? I need to just go on and show you this whole reaction. NH3, no, I'm sorry. No. NH4 plus and Cl minus. So HCl plus NH3 gives you NH4 plus and Cl minus. But now we broke that one up. We also have to break that one up. H plus, Cl minus. NH3 doesn't break up because it's a weak base. NH4 plus, Cl minus. The Cl's go away. Now this makes sense. This makes sense better now. That's your Lewis base, your base. It donates the lone pair to H plus, which is your H plus is your acid, your Lewis acid. Okay. Number 2, I don't need to do it because I did that at the very beginning. That was the first thing I did to show you H plus and OH negative, which is the Lewis acid and which is the Lewis base. Okay. Well, I'm getting through this quick enough, I hope. This is to be the last thing. Now, here is one, Al plus 3 and H2O. I wanted to show you this. I really, you know what? Al, I didn't really want to do this one. I wanted to show you a better one, but oh well. Al plus 3 plus H2O. All this is going to give you is Al, H2O, put 6 around it. It's a complex ion. Okay, so what's happened here? In the valence of aluminum, if I draw the Lewis dot diagram, remember aluminum has 3 valence electrons, but then it loses them all to be positive 3. Water, on the other hand, let's draw it this way and make it be clear. A water molecule is going to take its lone pair and adjust and attach to aluminum. Actually, 6 water molecules are going to do it. You have one at top, one on the top, below, left, right, front, back. And their lone pairs will attach just like that there and there. And so that would have to be your base, and that will be your acid. Lewis acid, Lewis base. Oh, well, that's good enough. And I've done all of them so far. I'll do the other one too, whatever. If you can turn it off now if you want, but we're done. Just do all those I showed you. There's a lot of things. Here, I'll show it to you if you need to take a screenshot. It's a lot of varied things. If you want to do all of it, you may. You don't have to do all of them. You can if you want. But I try to make it so that you're doing some things that are different. Okay, and here's the last one if you want to see it. SO3 and H2O. This is good as a equation prediction. You've seen SO3 plus H2O. You might remember, oh yeah, NOAA. Non-metal oxide plus water gives you H2SO4. You just add them together. SO3. Oh my goodness. I really don't want to. I don't want to draw this. You know, you guys, I don't want to take the time drawing it, but oh well. Well, maybe I will. Okay. This is going to be the base. That's going to be the acid. And because that's going to donate it. But SO3, remember how it goes. You have to do the ABC method. You know, you can go back and look at my Lewis dot, but it's going to end up having. Well, I can do it this way. I didn't want to go through the entire explanation of how I got this, but you'll find this in on my Lewis dot videos if you want to go back to Lewis dot diagrams. The SO3, that's how it looks, and so what happens is the H2O. This donates it to this one, and they attach to make H2SO4. Okay, and actually, when it does it, let me think about that for a minute. Yeah, that one H also pops off and joins onto an SO3, onto an O, the H's. Remember, I once told you how to do H2SO4. You got to do all kind of weird formal charge and all that. That's on a video too somewhere else. You know, I got that on the Lewis dot on the formal charges. Okay. Work all those. It's a lot of stuff. And then I think, is it next time math comes into play? Maybe not next time, but soon math will be there. All right, I'll see you guys.